In my talk, I am going to give a constructive approach to finding optimal degree in polynomial inequalities on semialgebraic sets. First of all, I would like to thank the organizers for the possibility to give a talk at the 16th International Workshop on Real and Complex Singularities. Apparently it takes place for the last 30 years, so great congratulations to the organizers. Okay, the subject of my talk is finding the optimal exponent in polynomial inequalities. Let us fix a semialgebraic set S in Rn and let f and g be two polynomials. We want to find the smallest exponent among the real d's such that f is less or equal up to a constant than g to the power d on S outside of a compact. Outside of a compact means that we're looking at the neighborhood of infinity, because complements of compacts can be seen as neighborhood of infinity, seen as a point. So in fact, once we look at f and we let g vary, this problem can be reduced to just finding the smallest exponent d such that f is less or equal than the dth power of the norm up to a constant on S outside a compact. And in this case, we're going to take this as the definition of the relative degree of f with respect to the set S. The optimal among such exponents that the inequality satisfies is exactly the degree of f relative to S and is denoted as deg SF. From previous work, we know that for a fixed set S, the relative degree of a polynomial is a maximum over a finite number of valuations. The maximum is taken over finitely many elements of a family of valuations, in fact semi-valuations, and this family of semi-valuations depends only on the set S, and the number depends on the degree of f. So in fact, if we have polynomials of fixed degree and the fixed set S, we have exactly a fixed number of fixed valuations such that their maximum realizes the relative degree of f. So in particular, we get that the relative degree, although it was optimal among any real exponent, similarly as in the case of Wojaziewicz exponent, which is given by the inequality reversed, is a rational number. In fact, what we can show is that the relative degree of f on a set S belongs to a discrete subgroup of the rational numbers because of special characteristics of the family of semi-valuations attached to f. The interesting case that we want to study is when S has non-empty interior. In fact, when S is fat, so it's closure of its interior, because any piece which is lower dimensional we can treat as a subset with non-empty interior of an algebraic variety, and so we reduce the problem to a fat set again. Okay, the motivation is in fact from the simple question, like we have some problems which are solved on compact sets. What happens if we want to get an answer to these questions on sets which are not compact? On a compact set, any polynomial is bounded by a constant, whereas on a non-compact, there is no such bound, but we still can find the rate of convergence of the polynomial with respect to the set S, which does not have to be necessarily its degree. So, for instance, one of such problems is constraint optimization problems, separations of sets that I will say a little bit towards at the end of my talk, polynomial representations, Markov inequalities, and other problems. We will explain a bit more towards the end of the talk, but for now the point is that the motivation inspires constructive methods, because the motivation, well, at least my motivation, is from concrete problems. So let us fix our attention for the moment on a family of sets such that admit easily a description of the relative degree. These are going to be weighted sets, meaning sets given by polynomial inequalities which are invariant under R plus action. So Z is going to be given as inequalities on quasi-homogeneous polynomials with a weight lambda. We will admit rational weights. That doesn't really change a lot if we think just about integer weights. Recall that a polynomial is quasi-homogeneous with weight lambda and degree w if g on points that we have acted by t to lambda, each coordinate is t to lambda I, the coordinate of lambda, multiplied by xi. The value of g on such coordinates is the same as an action onto the target. So t to w of g, exactly w being the degree with respect to this weight lambda. For short, we're going to write t lambda of x for the multiplication coordinate-wise of t lambda 0, x0, etc., etc. So we let lambda to have 0 or negative coordinates. That's important because it really makes a change in the geometry of the fibers. Any polynomial has a finite representation consistent with a filtration by weight lambda of the form f equal, and now we have quasi-homogeneous forms of degree j, whereas this degree can be just recovered as the scalar product of the weight lambda and alpha, which belong to the support of f. So one can think about the filtration in the space of lattice points of a of exponents of monomials as filtration by hypersurfaces which are orthogonal to the weight vector lambda. And this is exactly how we attain the representation of f as a sum of lambda quasi-homogeneous forms. Any weighted set can be seen as a union of the cube minus 1, 1 to the power n plus 1, and the finite union of unbounded sets of the form t acting on x with the weight lambda, where x belongs to z intersected with hyperplanes xj equal plus minus 1, and t letting t being bigger or equal than 1. One can always represent it in a union of sets of such form. The union doesn't have to be disjoint, but nevertheless it's the union. So in fact, it makes sense that we're looking only at the sets of the form t to the kappa times x, where x belongs to S and S is lesser dimensional set and t is bigger or equal 1. This form, as one can suspect, allows us to separate variables. So one is the variable t that acts with a certain weight, and the other variable is somehow fixed, where x belongs to n minus 1 n-dimensional less one-dimensional set S. So we reduce the dimension in the problem once we know how the weights and the original set interact. So let us have this set Sk of the form just said before. We have a theorem. So let us have a quasi-homogeneous polynomial with weight lambda. The degree of this polynomial is w, such that g does not vanish on the hyperplane on the set 1 times s, so on the lower dimensional set. For every f, the following two conditions are equivalent. F is less or equal than g to the power m up to a constant on s kappa, and so this is the inequality that we want. So what's the equivalent condition? An equivalent condition being constructive for all points in the support of f, where the support of f are all the lattice points such that the monomials with such an exponent in f have non-zero coefficient. So for all alpha in the support of f, we have that that all the forms in the decomposition of f with respect to the weight lambda are less or equal up to a constant than the nth power of g, but not on the whole set. We just need to look at it on the set 1 times s. And this happens for all the degrees of the forms in f. So for all j's, and j's are given by such equality. And the rest of the condition is that lambda alpha, for alphas from the support, is less or equal than lambda 0 w times m. These two conditions are equivalent for any rational number m. So, the corollary from this theorem is that if there exists a lambda quasi-homogeneous polynomial of pure positive degree on S kappa, then there exists a positive rational number such that the degree m module on Sk is given as the degree m module on S, well, as polynomials in the first variable x0 with coefficients from the degree m module on S, the lesser dimensional set, intersected with this half space. Well, not a half space. Yes, it's a half space. I'm sorry. Intersected with this half space spanned by all monomials that satisfy this inequality. What is this degree m module on S? It's just the set of all polynomials such that their degree is, with respect to S, is less or equal than m. And m can be any rational number, but as I said before, in fact, one has that the set of possible rational degrees is in fact a discrete set. So in fact, there is a discrete family of such non-trivially different modules. Okay, so to have this corollary, one needs an existence of lambda quasi-homogeneous polynomial of pure positive degree. What does it mean? It means that a polynomial is of pure positive degree on S if the Wejakiewicz exponent and relative degree on S are both equal. So the Wejakiewicz exponent is just the optimal exponent in an inequality which goes the other way around. Usually this inequality is taken with the distance from the zero set of G, but since we want to have a positive degree, we can just take the norm of X. And in fact, this condition is equivalent to the condition that G over the norm of X to the power m is proper on the closure of the set S for all powers m which are less than the relative degree of on S of G. So if we have one of these conditions satisfied, well, these conditions are equivalent, so if we have these conditions satisfied, then we have this structure of the module of polynomials of relative degree m. So examples of how we can apply the corollary and the more general theorem. So surprisingly, we can use this for all subsets of the real plane. For using this to all subsets of the real plane, one needs to have also the possibility of translation. So let us look at the theorem. So this theorem gives us a constructive representation of the module of degree m polynomials with respect to any semialgebraic subset of a real plane. So it's like in dimension 2, the description is complete thanks to our previous considerations. So if we take a semialgebraic subset of the real plane, there exists a curve C, arcs lambda 1 up to lambda L, integer points kappa 1 up to kappa L, and linear changes of coordinates. The curves and arcs, they are all semi-algebraic, such that the degree m module on Z is equal to the intersection of the degree m module on the complement of the curve in Z intersected with the module on the curve. Whenever we have a curve and we want to just say what's the degree of a polynomial, we just plug in the parameterization of the curve, and we can find the degree in a finite number of steps, because we don't need to plug in the full series of the parameterization. It suffices to plug in a finite expansion, let's say the singular part of the Puiseux parameterization. So in fact, we can already constructively say what the module on a curve is going to be. So in fact, the only thing we need to worry about is the complement of the curve in Z. And this can be given, as the second part of the theorem shows, as an intersection of these well-defined combinatorial objects. We apply the linear change of coordinates, and we apply a translation by a semi-algebraic arc gamma. So Lj is the linear change of coordinates. A gamma j is a translation by an arc. It's also a change of variables, but a trivial one. And we apply this to the spaces, well, to the space of all polynomials spanned by the monomials that are given by this inequality. So the monomials given in this half plane, given by kappa j, scalar product with alpha, because this is how I denote the scalar product, plus m, where m is exactly the degree of the module. So moreover, if z is fat, then the curve in this theorem can be taken as empty. So this is a constructive description, like all the objects in this theorem can be found constructively and also in a finite number of steps, which is very important for algorithmic considerations. And another special case is a wide class of weighted sets. Let Z be a set given by kappa quasi-homogeneous polynomials. Let's suppose that Zi is the intersection of Z with hyperplanes given by xi equal plus minus 1. Suppose they have non-empty interior, so again we're at the fat option. But here it doesn't have to be fat, because whenever we have non-empty interior, the interior is going to dominate the inequalities. And suppose that the P0 of Zi, meaning the algebra of bounded polynomials on Zi, is generated by monomials. As we can see, whenever we have a weighted set, it is going to be generated by monomials. So, well, monomials with coefficients from the previous iteration. So in fact, this gives us an inductive process of finding the algebra of bounded polynomials. But okay, the theorem says that the algebra of bounded polynomials in the set Z is spanned by monomials. Well, it's generated by monomials which have powers in lattice points belonging to a convex cone of the form, which is the following: an intersection of this over the support of all the algebras of bounded polynomials on Zi times the natural numbers. So remember that Zi is a one less dimensional set. So the support is necessarily in one less dimensional lattice space. So times j, and here I mean this thing here. I mean that we plug the natural numbers onto the jth coordinates. It should be I here. Zi, and here it should be I also. Sorry. And intersected with again, a cone spanned by this, by a polygon. So it's an intersection of half spaces given by such an inequality. This is consistent with already what we've seen before. A corollary is in fact that we can not only look at sets of type S kappa, we can also look at sets deformed by more complex actions, for instance, by beta a parametrization, so not only t to some power kappa, but t to kappa plus higher order terms. And let's say that this is a parametrization of an arc at infinity, with the order at infinity being a natural number, being positive. Then for this set, which is beta acting on x, meaning beta 1 times x1, beta 2 times x2 coordinate-wise t, so it's similar to this S kappa set, but, well, in fact, one can show that that only the order at infinity of beta is what dominates the inequalities in the description of the relative degree. So, in fact, with this more general set, we have that the degree of f with respect to the set is equal as the maximum over these inequalities where alpha d belong to the support of f. And we just take the scalar product of alphas with the integer point given by the orders f infinity of all the coordinates of f. Well, this is exactly what this order at infinity of beta is an n vector. Okay, applications. Because I said at the beginning that I wanted to do some applications of these theorems, so I'm going to state how the simplest application works. It's a simple extension of a Positivstellensatz. So if we have a set S given by inequalities, they don't need to be quasi-homogeneous. But in the quasi-homogeneous case, we have a description of the set of bounded polynomials. So we can verify easily the assumption that follows. So this set is given by G1, GL bigger or equal 0, such that they are bounded on S. So in the case of weighted homogeneous sets as given in the corollary before, we can verify whether they satisfy this condition in a constructive way. Then for any polynomial which is strictly positive on S, separate from 0, it doesn't have asymptotic values equal 0. For that, we need another condition, unfortunately. We have that it has a representation by sums of squares and powers of g. So this is a representation where g to sigma is just g1 to sigma 1 times g2 to sigma 2, etc. And SOS sigma is a sum of square of polynomials. So this kind of a representation is called the positive cone, TG. And in fact, so this is already an extension of the standard Positivstellensatz for compact sets to non-compact setting. But here we, instead of having polynomials like any positive polynomial, we need to have positive polynomials which are bounded on the set. And this is a nice substitution. More or less, the proof goes the same way as the original one. So more generally, like if we have a positive cone TG, does there exist a representation of F positive on S in the terms of TG? Okay, by Scheiderer, we know that there does not exist always such a representation if the algebra of bounded polynomials is just constants and all the BM of S are finite dimensional. I would like to note that here, for weighted sets, this holds, the second assumption holds. So we need only to verify the first. So we have already given some explicit necessary conditions of existence of representations during this talk, because it's easy to see whether a cone, which is whether an intersection of finitely many half spaces given in a combinatorial way has only has only the origin as the intersection, which is the same as saying that the algebra of bounded polynomials is just the constants. So recall from the theorem and corollary, we indeed had that the algebra of bounded polynomials is spanned by this cone, and we already had the BMs being spanned by such polynomials with such monomials as are described in the second part here. So we already know how to find the necessary conditions. So for example, the set ZA x squared minus ZB y to C, where C is even, has the above property. So not every positive polynomial belongs to the positive column. So we have a negative answer to the representation question, and also to, well, some constraint optimization problem. Another application is surprisingly to the idea of set separation. So during this talk, there was already, I already talked a little bit about the notion of polynomials of pure degree, which appear in several contexts quite surprisingly. So for instance, one of the contexts that you can use them is the separation of sets by a polynomial. So we take two semialgebraic sets, disjoint and closed. If they are both compact, then we can find a polynomial which is positive on one and negative on the other. So it separates, because it changes signs from one set to the other set, so the zero set of this polynomial separates these two sets. The question is whether this is true, for instance, if the sets are let open disjoint sets, so they can have some points in the common to the frontier, or, for instance, if they are not compact. So, well, does it hold whether they are not compact? No, it does not in general. But we have this theorem that if one set is given by inequalities, this is not restrictive in any means, and the other is any semi-algebraic set. They are both unbounded. If GIs are of pure degree on T, then one can separate S and T by a polynomial, and one can do it constructively. So, in fact, one can apply this theorem to sets, which I said in the beginning, to try to separate open semi-algebraic sets, so sets which can have some points common on the frontier. This theorem can be used in such a setting, but then we need to use something which is the relative multiplicity, and that would be, for another talk. So some open problems, well, I have not, didn't give result for all weighted sets, because there is an interaction with, let's say, there might be interaction in some cases. So for instance, I let go of the cases where in the set M that was given by the order at infinity of beta, where the order could be taken with negative coordinates. I let go of this. I didn't give any results on this. So in fact, one would like to have some results also in this case. There is also some work by Vietnamese mathematicians. I have given here two teams that gave papers, and they are using Newton polyhedra for principal sets, so for closed semi-algebraic sets given by an inequality f bigger or equal than 0. And then one can find the relative degree of polynomials in terms of the Newton polyhedron of f and of g, how the slopes interact, more or less. This is really interesting talk. This is interesting work of theirs. And of course, as I said, so there already were some results on polynomials of pure degree, and they crop out in surprising applications. So I think this is also an interesting idea to pursue. So thank you all for your attention. Thank again the organizers, and well, thank you for listening to my talk.